Yes.
Okay. No, just visited a few times. Okay, good. Good morning, everyone. I hope you're doing well. So what we were talking about last time were distributions, and we kind of had two different things in mind. One was discrete distributions, and these were ones where if you're going to do some kind of measurement, a discrete distribution means that there's only a finite set of possible outcomes. So like the easiest examples to think of are rolling a die or drawing a card or something like that. And so in that case, we came up with a whole bunch of different possibilities for expressing the mean and standard deviation of a distribution. So for a discrete distribution, first of all, if we sum over all of the possible outcomes. So remember, there was a distinction between, we were using little n to represent the number of possible outcomes. So like rolling a die, there's 6 possible outcomes. And then we used capital N to represent like the number of trials of an experiment. So we could roll a die 10,000 times, right? And so here, if we sum over the probability of all the possible outcomes, we have to get 1, right? The probability of getting a 1 when you roll a die, plus the probability of getting 2, plus 3, plus 4, and so on. And then we worked out that the average of those results from our experiment could be expressed as the sum of the possible outcomes times the probability of getting that outcome. And then the standard deviation, or the square of the standard deviation, had a similar definition. Instead of just x here, we put the difference between the value of the outcome and the average. And then we just worked out that we could write that in a second way if we wanted to. Okay, and then we said, okay, well, we also have continuous distributions. This is where we do a measurement and there's no restriction on the result of that measurement. It could take on any value. Some of those values might be extremely low probability of occurring, but you could have any result for x along some continuum. Okay, in that case, we had probability distributions where, you know, the units of the probability in this case, what would the units of this probability for a continuous distribution have to be? What would the units have to be? Like we need to overall get something that is no units. What are the units of dx? 1 over meters or something, or sorry, dx is in meters. So then this probability has to be units of 1 over length. or let's say 1 over the units of whatever the units of x are. You know, x, we usually use x for length, but here it represents anything. Okay, so that's just something to keep in mind. This, for a continuous distribution, is called a probability density. So it's a probability per unit something, and that something is whatever the x is that we're measuring. Okay, other than that, everything else looks the same, except instead of having a sum over discrete values, we have an integral over a continuous range of values. So what I want to do is I just want to do some examples where we work with some of these things. We'll start with an example using a discrete distribution, and then we'll do an example using a continuous distribution. So the only other thing that I have written down here is that for a continuous distribution, you know, maybe the probability density has some funny shape like this. And what we said is for a normalized probability distribution, if we integrate over all values of x, we have to get 1. So the total area under this has to be 1. If that's the case, then if we pick a little sliver of area, what it tells us is that if we take that height, we approximate this as like roughly a rectangle. We take the height of that rectangle, multiply it by its width, and the width here is just delta x. Then what that tells us is that shaded area is the probability of obtaining a result for a single measurement, single trial that falls between this xj, whatever that is, and xj plus delta x. Okay, so let's try an example. So let's try an example with a discrete distribution. And so what we're going to do is we're going to make up a game. And so the game is going to be the following. You have dice, you have 2 die. And so you're going to roll them. You know, you can get 1 through 6 on each of these die. So roll a pair of dice. And so, you know, you can get D1 is 1, 2, 3, 4, 5, or 6. And D2 is 1, 2, 3, 4, 5, and 6. Okay, and so here's how the game's going to work. What we're going to do is we're going to take the difference between these outcomes, and we're going to give you money depending on what that difference is. So outcome 1. If we take the difference between the 2 numbers, and let's just take the absolute value of that difference. And if it's greater than or equal to 3, then we're going to pay you $1. Okay. Outcome 2 is that if the difference, or the absolute value of the difference, is between 1 and 2, well, I mean between 1 and 2, if it's 1 or 2, then you're going to get a different amount of money. We're going to pay you $2. And then the last possible case is if D1 and D2 are equal so that their difference is 0, then we'll pay you $3. So the smaller the difference is, the more money you get. Now the catch is that in order to play this game, you have to pay me $1.75. Okay, so we have to pay $1.75 for each play. And so the question is it worth it? Is this going to be a profitable endeavor? Okay, so is it worth it to play? All right. So what we have to do in order to solve this problem is we have to figure out what is the average amount of money that you're going to get. And if that average amount of money is bigger than $1.75, then we should play this game as much as possible. We might lose money in the short term, but if we kept playing and the average payout was more than $1.75, you know, it's a cash cow and we should just keep going. All right. So if the average amount of money earned is greater than $1.75, we should play. Okay, so how are we going to calculate this average? The average is going to be, so the sum over all possible outcomes of, well, it's MI times the probability of outcome MI coming up. Okay, so what we need to do is, in order to do this calculation, we need to know the probabilities of the three outcomes. We've already written down that there's three possible outcomes, so n equals 3 in this case. And the rules of the game were that we get different amounts of money and we know what they are. They're $1, $2, and $3. So our task right now is we need to determine the different probabilities for the different outcomes. Okay. So the way we're going to do it is the following. This is one way to do it. I'm not saying it's the only way or even that it's the best way. But what we're going to do is I'm going to have, say, the outcomes of D1 along the column here. So 1, 2, 3, 4, 5, 6. Okay. And then we'll have the outcomes of D2 horizontally. And it would be 1, 2, 3, 4, 5, 6. Okay. And then what we care about is the difference between the outcomes. And so I'm going to fill in this table with the absolute value of, say, D2 minus D1 or D1 minus D2. It doesn't matter. All right. So first, let's just find where all the zeros are going to be. The zeros are going to be the one that pay out a lot of cash, right? And so we would get $3 if we rolled 2 1s. We would get $3 if we rolled 2 2s and 2 3s and 2 4s and 2 5s and 2 6s. So those are all the payouts of $3. All right. Then if the difference came out to be a 1 or a 2, we're going to pay you $2. So we would have like 2 minus 1 would be a 1, and that would be a $2 outcome. So this would be a $2. And then a 3 minus 1 would also be $2. But then when we got to 4 minus 1, that's 3. And if we get a 3, 4, 5 as a result, that's a $1 payout. So that's a loser result, right? So we lose 75 cents. Okay. Well, so let's just keep filling this in. 5 minus 1 would be a 4. 6 minus 1 would be a 5. Okay. And then we do 2 minus 1. That would be a 1. That's $2. And then we'd have 3 minus 2 would be $2. 4 minus 2 would be a 2. That would be $2. And then 5 minus 2 would be 3, and like so. Okay, and then we just keep going. 3 minus 1 would pay out $2. 3 minus 2 would be $2. 4 minus 3 would pay out 2. 5 minus 3 would pay out 2. And then 6 minus 3 would pay out 1. All right, and then I think you could probably see what's happening is that the neighbors of the $3 payout, the two neighbors of the $3 payout are $2, right? So this is 6 minus 4 is 2, and it pays out $2. And then you could just go and fill in the rest of this table. This would be, oh, let's see. 5 minus 2 is 3. 6 minus 2 is 4. 6 minus 3 is 3. Then I think the rest are $2. This is 6 minus 5. This is 5 minus 4. 5 minus 3. This is 6 minus 4. 6 minus 5. Okay, there we go. So that's the table that summarizes all the possible outcomes of our game. And there are 6 by 6, so there's 36 entries. So there's 36 entries. 6 of them along the diagonal pay out the $3. So there's 6 ways to get M3 equals $3. So that means P of M3 is the 6 possible ways divided by the 36 possible outcomes. And so that's 1/6. Okay. How many ways are there to get $2? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it should be symmetric, so there should be 18 of them. So there's 18 ways to get M2 equals $2. And so PM2 should be the 18 ways divided by the 36 possibilities. And so that's 1/2. Okay. And then to get $1, we have 1, 2, 3, 4, 5, 6. And then there'll be 6 in the opposite corner. So 12 in total. So we should have then that 12 plus 18 is 30 plus 6. Yeah, that adds up to 36. So that's good. Okay, so there's 12 ways to get M1 equals $1. And so PM1 equals 12 over 36, which is 1/3. Okay, so now we have all those probabilities and we can find the average payout. So the average payout is the sum of I equals 1 to N equals 3 of MI, P of MI. And so the $1 outcome has a probability of 1/3 plus the $2 outcome, which has a probability of 1/2 plus the $3 outcome, which has the probability of 1/6. Okay, so let's put things over a common denominator here. I guess 6 being the common denominator. So we would have 2 plus 6 plus 3, I think, over 6. So yeah, 2 over 6 would be the 1/3. 6 over 6 would be 1. And 3 over 6 would be, yeah, 3 over 6. So that's good. Okay, and so what is that? That's 11 over 6, which is $1 and 5/6. And so what's 5/6? Is it 833333333? So it's more than $1.75. So you should be playing this game. You should drop out and play this game. Okay, so this is more than $1.75. So it's profitable. Okay, so that's just a silly example, but what it does is it tells you kind of the procedure that you would have to take in order to do this. And you know, the procedure really was to first figure out the probabilities. After we have the probabilities, then we're just doing a sum. And you know, you could make the thing more complicated. You could say, well, I'm going to have unfair die, and so the probabilities are going to be adjusted. You could even have different probabilities for the different dice and so on. So you could make this arbitrarily kind of complicated. You could also calculate the standard deviation, and that would be easy to do because we already know the probabilities. And so if you wanted the standard deviation, you would do the xi, the outcomes, minus the average, which we now know, square it, times by the probability, add them up, and then take the square root in the end. So exercise for the students. Show that sigma squared, which is equal to the sum of I equals 1 to n of, well, it would be xi minus mu squared p of, oh, maybe I'll put the m in there because we've been using m for like money. P of mi. So you do this calculation, and what you should find is that sigma squared is 17/36, or sigma is 0.687. And that's in dollars. And so the standard deviation is, you know, 69 cents or something like that. And so you definitely could lose money. Like you could play your first 100 rounds, you might find, oh, I'm down $10 or something like that. But if you just keep at it, you will make up that difference. Okay, good. Any questions about this example? All right, so what I want to do then is I want to now try an example using continuous distributions, and we'll make this one like a more physicsy example. Okay. So we'll do a continuous distribution example. All right. What we're going to do is we're going to try to figure out the average distance that an electron is from the nucleus in a hydrogen atom. Okay, so here, let me just find the right example here. Okay, so the probability that an electron is a distance r from the nucleus of a hydrogen atom is, okay, so PR dr is C r squared e to the minus r over r dr, okay, where C and big R are constants. Okay, so what we want to do then is a couple of things. First of all, we would like our probability distribution to be normalized. So we want its total area to be equal to 1. So what we're going to do is we're going to enforce that, and we're going to set the value of the constant C to guarantee that the area under our distribution is equal to 1. So question A is to use the requirement that the integral of PR dr equals 1 to find the value of C. Okay, so what we're going to do is we're going to say, okay, the integral of PR dr is going to be equal to the integral of C little r squared E to the minus little r over big R dr. Now, the first thing we have to do is we have to pick the appropriate integral limits. And so for this problem, where we're thinking about the distance of an electron from the nucleus of a hydrogen atom, what are the possible values of this little r, this distance? 0 to infinity, right? We can't have a radial distance that's negative, okay? So just because we have a continuous distribution, it doesn't mean that all possible values of r are allowed from like minus infinity to plus infinity. It just means that over whatever the allowed range is, we could get any possible outcome. There's no discreteness within that range of possible values. Okay, so therefore, we want this to be equal to 1. What I could do is I could take up the C and I can divide by it, and I'm going to do that. So I'm just going to say 1 over C is equal to this integral of r squared e to the minus r over r dr for r equals 0 to infinity. All right. How are we going to solve this integral? Product rule, integration by parts, that's right. Yeah. So whenever, integration by parts, maybe there's several situations you can use it. The most common one is an exponential times some power. Okay, so we're gonna integrate by parts. Okay, and so what we'll do is we'll say, all right, I'm going to set that to be r squared, so that du is 2r dr, and dv is going to be the rest of the stuff. So it's going to be e to the minus r over r dr. And so that means v is, I have to integrate this. So it must be minus r e to the minus r over r. Yeah, that's right. Because if I take a derivative, I'll get a minus 1 over r. I'll cancel this thing, and I'll take off the key r. Okay, good. All right. So integration by parts. I'm sure you all know this, but what you do is if you have u dv to start with, that is going to be uv minus the integral of v du. And so this, most people remember that. What a lot of people don't remember is that if you're doing a definite integral with integration limits, then of course the limits carry over, but you also have to evaluate this product here between those limits. Okay, and so let's just do that. So 1 over c is going to be equal to u times v. U is r squared, v is minus r e to the minus r over r. That's going to be between 0 and infinity. And then we have minus the integral of v is minus r. And then we have a 2r from our du, e to the minus R over R dr. I think that's probably right. Okay. What's this first term going to be? 0. So if I put in the bottom limit, I get 0 squared times e to the 0. So that's just 0 times 1 is 0. If I put it in infinity, I get infinity squared, but then e to the minus infinity. So how do I know that that's 0? Yeah, you would do L'Hopital's rule, right? Where you take derivatives of the two quantities like r squared over e to the r over r. And as you take the derivatives, the power is just gonna go away. It'll eventually just become a 1. But you'll always be dividing by e to the infinity, which is always going to give you a 0. Another less technical way of thinking of it maybe is exponential goes to 0 much faster than r squared goes to infinity. Okay, and so this thing here is just going to vanish. And so what we have is 1 over c is equal to minus. So it's a plus because we have minus minus. We have a 2r up front. R e to the minus r over r. I've got bad news for you. Got to do it again, okay? And it's only going to get worse. So, all right. So, Christ's sake, we'll integrate by parts again. Integrate by parts again. So let's do it fast. U is r, du is dr, dv is e to the minus r over r dr. V is the same. It's going to be minus r e to the minus r over r. Okay, so 1 over c is equal to 2r times some stuff. uv minus r e to the minus r over r, 0 to infinity. We already know that that's going to be 0. So let's just put it at 0. And then minus b du. So the minus sign is going to cancel. So I'll just write it as a plus. We'll have an r, which we'll take it. I'll just pull it outside the integral now. And then we have the integral of e to the minus r over r dr. Okay. So we have 2r squared. And now we can do this integral. I guess we're going to pick up a minus r e to the minus r over r. Tell me if I'm making a mistake. I think this might be right. Okay, between 0 and infinity. All right, when I put in the limit of infinity, we get e to the minus infinity, 0. So we end up with 2r squared. Let's see. Infinity 0 minus minus r e to the 0, which is just going to be a 1. So we just end up with a 2r cubed, I think. All right, good. And so therefore, c is the inverse of that. So it's 1 over 2r cubed. So it's quite a bit of work just to get our normalization constant. But anyways, that's what you would do. And so now we know that our probability distribution will have an area underneath it of 1 if we keep c set to 1 over 2r cubed. Okay, so this is the normalization constant. All right. So what I want to do next is I want to find the average distance that our electron will stay away from the nucleus. So that's going to be part B. Find the average distance, let's say r, that the electron is from the nucleus. Okay. Well, for our continuous distributions, the average distance was r times p of r dr. And we know that we've already decided that the allowed values for r, the radius, is 0 to infinity. And so this is the calculation we have to do. And brace yourself for some more bad news, because we're going to have r times our probability distribution, which was c. Let me look it up here. I think it was c times r squared, wasn't it? Yeah. Yeah, c times r squared e to the minus r over r dr. Okay, and that's going to be c, the integral 0 to infinity, r cubed e to the minus r over r dr. Integration by parts again. Okay, and what we're going to be a little bit clever about how we do this, because we've already integrated by parts twice. And so I want to limit how many times I have to do it. If I was to do this question blindly, I would integrate by parts, and I'm going to end up with something, and then r squared e to the minus e to the r over r. And then from there, I could integrate by parts again to make this an r times the exponential, and then integrate by parts again to make this just the exponential. However, what we're going to do instead is we're going to say, we'll integrate by parts once. That's going to bring us to an r squared times this exponential. But I already have that result, and we'll just use it. Okay, so integrate by parts. Let's see, u is r cubed, du is 3r squared dr. The dv and the v are always the same. V is going to be what? Minus capital R, e to the minus r over r. Okay, so the average value of r is c times. Let's see, uv. The uv is hardly worth writing down because we know that it's going to be 0, but we'll write it down anyways, I guess. Okay, that's going to vanish. Okay, and then we would have minus v du, but the minus signs will cancel, so we'll get plus r. In fact, we'll get a plus 3r because we're going to get a 3 from the du. And then we would have the integral of 0 to infinity r squared du. So yeah, sorry, exponential from the v, and then we just have a dr. Okay, and this is the place where we're going to save ourselves a bit of time. Okay, so this second integral, r squared times this exponential, if we just scroll back a little bit, r squared times the exponential, that's the exact integral we have to do. And in fact, the way we've set it up, it's kind of neat. I don't even need to look up the result. I just have to know that that's 1 over c. Okay. So we know that this is 1 over c from question A. And it's kind of nice because we have a c times a 1 over c, and they're going to exactly cancel. And so therefore, the average distance from the nucleus is 3 times r. So this is the average distance of the electron from the nucleus in a hydrogen atom. I mean, I keep writing from the nucleus, but the nucleus of hydrogen is just a proton. So it's the average distance between the electron and the proton in the hydrogen atom. Okay. Let's do a little bit more. How are we doing time-wise here? We have like 12 minutes. All right. So let's see. We can then do part C, and let's find sigma for the electron in the H atom. Okay, so sigma was equal to the integral of, let's see, r minus, I mean, I guess we usually write it as mu, so let's go r minus mu squared p of r dr. R goes from 0 to infinity. Okay, instead of doing this calculation, I want to show you how we could rewrite this. And we did it for the discrete distribution, but let's do it for this thing right now. So we'll first just evaluate the square, expand the square. So we would have r squared minus 2 mu times r plus mu squared p of r dr. Okay, and then we'll distribute the integral. It's r squared p of r dr is the first one. Then we'd have minus 2 mu. And we'd have the integral of r p of r dr. And then we'd have plus mu squared. I'm going to move that over. Plus mu squared, the integral of 0 to infinity dr. All right. What's this integral? We just did it in part B. Yeah, it's the average position of the electron. We called it R average, but this could just be mu. It's also equal to R average. Okay. What would this integral be? Yeah, that's part A. And so what we did is we chose the value of C so that we would force this integral to be equal to 1 for our normalized probability distribution. And so that means I have to be careful. This is sigma squared. So the sigma needs a square on it. I missed that. Okay. So then what we have is sigma squared is equal to the integral from 0 to infinity, r squared p of r dr. That doesn't change, but now we have minus 2 mu times mu. So minus 2 mu squared plus mu squared times 1. And so overall, it's just a minus mu squared. And I don't know if you've seen this before, but if r times the probability distribution and then integrated is the average value of r, what's r squared times the probability distribution and then integrated? Average of r squared. That's exactly what it is. And so this is the average of r squared. And this one is the average of r. And so therefore, one way to express the standard deviation, or the square of the standard deviation, sigma squared is equal to the average of r squared minus the average of r all squared. And so this always works. Like, it doesn't have to be the radius, right? It could just x representing anything that we measure. If it follows a probability distribution, the standard deviation is x squared averaged minus the average of x squared. Okay. So what we want to do then is to complete this calculation. We've already done this one. So what we have to do is to find the average of r squared. Okay, so we need to find r squared averaged, and we already know that the average value of r was just 3 times capital R, right? Okay. So it's r squared times the probability distribution, like so. And this is going to be the integral from 0 to infinity of c, which we know, I think it was 1 over 2 times r cubed or something like that. C times, it was r squared, and then times r squared. So this is r to the 4th, e to the minus r over r, and dr, and then you have to integrate by parts again, and you say, oh goddamn, I'm tired of integrating by parts. So this is an exercise for the student. Now you want to be efficient, right? We've already done the integral of r cubed e to the minus r over r. So we would just want to use that result. If we just look back here, where was it? Yeah, it's this thing right here. Okay, and we boiled it all down, and we realized that it was like there's the c out front that I don't care about right now, but this integral is all of the stuff in the brackets, and it just came out to be 1 over c. Okay, so oh, I have to be careful. It's 1 over c times 3r. So let's just make a note that we know from part B that, let's see, we'll eventually be faced with this integral. And let's see if we could figure out what its value must have been. Yeah, it's everything except the c here. So it's 3r divided by c. Okay, so this is 3r divided by c, and we know that c was 1 divided by 2r cubed. Is that right? Let me see. Sorry for scrolling. Yeah, 1 divided by 2r cubed. And so this is going to be 3 halves r to the 4th. All right. So that's just a bit of an aside. And so the exercise for the student is that I know that I think that show that r squared averaged is equal to 12 r squared. Oh yeah, you're right. Yep. Thank you. Good. Okay. I'm pretty sure that this is right. So give it a try and see if you could figure it out. See if you could confirm that. So then sigma squared is the average of r squared minus the average of r squared would be 12 r squared minus 3r is what we got for the average, and then we have to square it. So this would be 9r squared, and so this turns out to be 3r squared. So therefore sigma is equal to the root 3 times r. And so standard deviation, what it tells you is, it tells you that 68% of the time, you're going to find your electron within 1 standard deviation of the mean. So we know the mean is 3 times big R. And so that means that we'll be within that value well, let's see, will be between, maybe I should write it down, because if I say it, it's gonna sound dumb as hell. Okay, so we know that a measurement has a 68% probability of falling within one standard deviation
And it will always be 68% in one standard deviation.
of the mean. You know, I guess I should be careful. This would be for, this result is strictly speaking for a Gaussian distribution. And so we don't have a Gaussian distribution, but it's probably similar to this kind of result. So you're absolutely right, is this is for a Gaussian distribution. So can I say that our electron will be within one standard deviation of 3R, 68%? I can't say that, but it's probably something similar to that. You probably have to fine tune the percentages or something like that. But yeah, you're correct. And that's a good thing to clarify. And it's also time to stop here. Okay, good. So that was a bit of practice using some of these results for discrete distributions and continuous distributions. Where we're headed over the next couple weeks maybe is just looking at some specific examples of common distributions. We'll start with the binomial distribution for a discrete case, and then we'll think about Poisson and also normal distributions or Gaussian distributions. All right, perfect. Thank you very much.